So, in the last lecture, we went through the exercise of trying to find the force acting on a spherical particle that was executing some unsteady motion. So, there was an unbounded domain, a particle of radius a, and this particular spherical particle was executing some kind of an unsteady motion, and accounting for the unsteady acceleration term, we arrived at that the force acting on the particle obviously has the quasi steady Stokes drag term, which tells us that the drag force right now depends on the velocity at this instant of time. But then we also encountered two new terms that came in the problem. The next term, which is actually a term that has to do with the acceleration of the fluid. So, or the particle in this case. So, the fluid is at rest. So, if the particle is accelerating, the next term that we had for a spherical particle is the mass of the fluid displaced into the acceleration, half of that. So, this is known as the added mass force that the particle is experiencing. So, this is again an instantaneous effect, which tells us that the force that the particle experiences depends on the particle's acceleration at that particular instant. And then the last term, which was the new discovery in this exercise, that was a term that is non-local in nature. This particular term tells us that the drag force at a particular instant depends on the fluid acceleration, or here the particle acceleration over all the past history. Now, this exercise effectively gives us that if I look at the added mass force and I inspect the history force, the added mass force, as I was mentioning earlier, is what you also obtain when you solve the problem of potential flow. If you were to take the same spherical particle and make it move in an unsteady manner, you would encounter that same added mass force that this object is going to encounter. Now, the fact that this is instantaneous, the force at that particular instant of time is instantaneous, that comes from the fact that this particular force is generated due to the velocity potential which is obtained by satisfying the normal boundary condition. So, imagine that I have a spherical particle of radius a and I was to move this particular particle with some velocity u of t. Now, at every point, whether you do a potential flow problem or you do a viscous problem, the normal boundary condition needs to be satisfied, which means that the fluid boundary, the fluid velocity, its normal component should be equal to the normal component of the particle velocity. That is my no penetration boundary condition. So, if I make a change to the boundary, which means that this u suddenly changes from a value, let us say u1 to u2, which means there is an immediate change in the normal boundary condition. Whatever is your no penetration boundary condition suddenly has a change. Now, if you go back to potential flow, how quickly is this change going to get transmitted? How quickly will the fluid realize that there is now a change in the normal boundary condition? Will it have a certain time scale over which it will happen, or will it be instantaneous? So, the question is more to do with potential flow, and then we will draw the connection to the low Reynolds number problem. In potential flow, when you solve this problem, you were solving Laplace equation subject to the boundary condition that dou phi dou n should be equal to u dot n. U bar is basically the velocity with which the boundary is moving. So, if u bar, the velocity of the boundary were to suddenly change, it was accelerating or decelerating, how quickly would the solution for the potential change? Will it be instantaneous or will there be a lag? It will be instantaneous. Any change of normal boundary condition gets propagated instantaneously in potential flow. You make the sphere accelerate, you make the sphere decelerate, whatever you do, the change in the normal boundary condition, if it happens, it gets instantaneously reflected in the solution. Now, why is that happening? Why should it get reflected instantaneously? What is it that we are doing here which leads to this instantaneous propagation of the disturbance? Are we assuming something? Think of an extreme example. This spherical particle was effectively moving with a certain speed and suddenly it accelerates to a very high speed. If it was moving in an air-like medium, imagine that it went from a speed of 20 meter per second to 600 meter per second. What would happen in the real problem? In an actual problem, what would happen? If there is a sudden acceleration, what is the consequence of that sudden acceleration in the actual problem? You have a particle that is moving, assume air, the flow is potential flow, and ignoring all viscous effects that you can think of, and the spherical particle suddenly accelerated from 20 meter per second to 600 meter per second. What do you think would happen in the real problem? What has happened to the motion of the particle? Is it larger than any characteristic speed that you are aware of? It is moving now faster than the speed of sound, right? So, if it is now moving faster than speed of sound, what would you see in the problem? What effects would you see? There would be shock waves that would basically appear, right? So, effectively what I am trying to say here, that there is a finite propagation speed that is there in a fluid, and that finite propagation speed is the speed of sound waves, acoustic waves, right? So, when we are doing this problem in the incompressible limit, what is the speed of acoustic waves? Mathematically, what is it? For an incompressible flow, what would be the speed of acoustic waves? It's infinite. The speed of acoustic waves is infinite, and because it is infinite, which is why you have this immediate adjustment of the flow to any change of normal boundary condition. So, the reason for all this discussion is that the added mass force in an incompressible fluid is only dependent on the instantaneous acceleration. It is not dependent on the history of acceleration. Whereas the viscous force, which is what you are seeing here, this viscous term is coming because you have to also satisfy the no slip boundary condition. And viscous waves, unlike acoustic waves, do not travel with infinite speed when you are basically accounting for the unsteady term. So, in Stokes flow it is infinitely fast, but when you are doing unsteady Stokes flow, then the speed of propagation would be, what would be the speed of propagation for a viscous wave? So, if you say tau is a time scale or t is a time scale, if you say square root nu t is the length, right? So, length by time, which means this would be the speed of viscous waves. That is the speed with which information is actually propagating. So, that is the reason why you actually have a non-local term coming from your viscous effects, whereas the added mass term you can think of it in terms of satisfying the no penetration boundary condition, which you could have done also in the inviscid problem. And there we know if it is an incompressible fluid, information propagation happens infinitely fast, because you are inherently saying that the fluid being incompressible implies that the speed of sound in that medium is infinite. So, it will be instantaneous, and thus the added mass effect is only dependent on the instantaneous acceleration. It is a local term, whereas the integral term that you have here, this integral term is a non-local term. So, this is an important point to actually pay attention to, that even though when you do all these algebra, sometimes you can lose sight of where each term came out from, but the fact is the locality or the non-locality of the different terms in the force has some meaning in terms of how information is actually being transmitted. Because obviously if an object is moving unsteadily, both normal boundary condition and tangential boundary conditions are changing unsteadily. So, what we are trying to do is, in some sense, we are trying to separate out the change in the normal boundary condition and the tangential boundary condition. The change in the tangential boundary condition is something that you can view in terms of creation of vorticity. Go back to the problem that we did at the beginning of last lecture. Take a flat plate, an infinite, this is the classical impulsively pulled plate problem. You take this plate and you make it move. So, when you make it move, what you are doing is you are changing the tangential boundary condition in an unsteady manner. We never say specifically normal and tangential in this problem, because we are only solving for an equation of the streamwise velocity. We do not solve for the normal component, because we say that the normal component is 0 at the plate is not moving in the normal direction. So, if the fluid was at rest and if the flow does not change in x direction, uy is 0 everywhere. So, we immediately skip and start focusing on the flow component that is in the x direction. So, this is the tangential change in boundary condition, and a tangential change in boundary condition is going to lead to production of vorticity. What is vorticity? Vorticity, if I think of a simple scenario of a coordinate system where this is x, this is y, then the vorticity would be dou uy dou x minus dou ux dou y. In a local Cartesian coordinate system, this is what will be the vorticity. So, imagine this is actually a zoomed in version of a particular part of the sphere. So, locally you can have an x and a y coordinate system, and now you can see that the tangential change in velocity. So, when you make the sphere move, the tangential change in velocity is leading to production of vorticity, and that vorticity is diffusing out at a certain pace, and that is given by your viscous waves. In Stokes flow, that propagation happens instantaneously, but when you do unsteady Stokes flow, the vorticity diffusion is happening at a certain finite pace. Whereas, if you have a normal boundary condition change, that is primarily being dictated by the speed of acoustic waves or sound waves, and obviously we are doing an incompressible flow, in which case this is going to happen instantaneously. So, this is a way to basically break out dissect what the different contributions are. Now, this was an exercise in terms of trying to find out the force that is experienced by a spherical particle moving in an unsteady manner at very low Reynolds number, but the fluid is quiescent. So, what we will do next is we are going to start removing some of these assumptions and making the background flow a little more complicated. But before that, it is important to actually pay a little attention to the history term. So, this term is often known as Basset history. There are many others also associated with doing this work, but for the time being I will just focus on that particular term. So, if you look at that term, minus infinity to t, and if I write this as t minus t prime du dt t prime dt prime where this kernel is 1 by, actually I will write it with a pi nu t. If I put a pi and nu here, then this becomes 6 pi mu a square. So, what I have done is I have written this term as an integral over the acceleration over all. So, t prime goes from all points in the past to the current instant of time, and then this is the kernel that you have. Now, the question is, if you look at this particular kernel, this kernel is actually going as 1 by root t. I am using tau here. So, let me just, let's do one thing. So, I will have, so I am just going to write the time dependence. So, this particular kernel is decaying as 1 by root tau. Now, what do you think is peculiar about this kernel, or if you are thinking in terms of numerics or calculation of this kernel, what do you think is possible challenges with this kernel? When tau goes to 0, what happens to the kernel? It goes to infinity, right? This kernel is basically diverging as t prime approaches t, right. As you are approaching the time instant t, the kernel is basically going to diverge. Now, that might appear worrying, right. Whenever you do an integral of a function, think of it numerically. Whenever you do a function's integral, and if the, imagine like a trapezoidal kind of a rule. So, this is a function of tau and you are breaking this into lot of rectangles and you sum this over, the simplest way to do a numerical integration. Now, if the function were to actually start blowing up, then it becomes worrying, right, because how do you add these rectangles? Now, you have to remember this is actually a sum of the function, let us say at the ith point, into some delta tau, correct. So, if the function actually goes as 1 by root delta tau as it goes towards the origin and the base of that rectangle is delta tau, then what happens? The area of that tiny rectangle close to the origin is not going to blow up, because the height of the rectangle is diverging, but it is diverging at a slower rate than the rate at which the other dimension of the rectangle is actually shrinking. So, the area actually goes to 0. So, even though you have this kind of a worrying signature of that kernel, it does not make any problem, create any problem here, that finally the contribution from that region is not going to give rise to any divergence. So, it is actually a convergent integral because of that nature of that singularity. But the issue is not actually at tau equal to 0. The issue comes at when tau goes to infinity. Tau going to infinity means what? Tau going to infinity is equivalent to t prime basically being at the other limit minus infinity, right. Now, why is that an issue? Imagine the acceleration was a constant. The particle was accelerating with a constant rate, or has had a constant acceleration, the velocity was increasing linearly. Then you are going to do an integral which is minus infinity to t k nu t minus t prime dt prime. If I do a change of variable, this substituting for tau is equal to t minus t prime, then the lower limit becomes infinity, upper limit becomes 0, correct, and then I have k nu tau minus d tau. Now, this is 1 by root tau. What is the issue? with this integral? 1 by root tau d tau going from 0 to infinity. This is divergent, and the divergence is actually coming from infinity. So, the tail is where the problem is. Initially, you would have thought that the problem numerically should come from the time instant which is very close to the present time instant, but actually the issue is coming from significantly far away in the past. So, those contributions become a challenge numerically to integrate when you are trying to do this. So, we will towards the end of today's lecture, we will touch upon this point, because you can start thinking, how do we address this? How do we address this fact when I am thinking of acceleration significantly far away in the past? Because that is what is leading to this kind of a challenge. And what you can start to anticipate based on the topic we covered before unsteady flows is that once you have moved at distances significantly large in space, what happens? If you have moved away from the sphere significantly large distances, inertial forces can no longer be ignored. The convective inertia term cannot be ignored. Now, I am saying space and then I am saying time, and they are related, because if it is moving in time and you are trying to relate a point in time significantly in the past, that time is basically located upstream at a significantly large distance. So, the inertial effect from that region cannot be ignored. You are still treating in the current formalism that that point in space is still governed by unsteady Stokes equation, which is not accurate. So, that is where we will come after doing the summary of all the forces that are there. So, that is the part regarding the Basset force. Now, as I was saying that this was done where the sphere was moving with some velocity u of t, right. The sphere had a radius of a, it was moving with a velocity u of t. Now, what if there is a constant magnitude or a uniform flow of u infinity of t? So, it was not a it is not a spatially varying flow, it is a flow that is uniform in space, but changing unsteadily in time. What would be the change of the force that it experiences? Now, how do we do this? So, one simple way to do this is you fix your coordinate system that is glued with this flow, right. So, this flow, the background flow, is satisfying now. Will all the terms be there in Navier-Stokes for the background flow? It is satisfying Navier-Stokes, also divergence of u infinity equal to 0, but will all the terms exist in Navier-Stokes if the background flow is just a uniform flow varying in time? Which terms would be 0? I am again repeating, this is a uniform flow. What does it mean? Spatially no variation. So, this term is 0, this term 0. So, the governing equation for that uniform flow is that the fluid acceleration for the background flow is balanced by some pressure gradient, okay, and obviously it is divergence free, that goes without saying. So, now I am going to define the total velocity field, and this is, you might be reminded of what we did in calculation of stresslet and similar problems. Let me not put a prime, as a sum of the background flow plus a disturbance. This is the perturbation to the background flow or a disturbance to the background flow. Similarly, your total pressure would be P infinity plus some disturbance. Now, if I am in a reference frame which is moving with u infinity, what is the velocity field in that reference frame? It should just be u, right? The disturbance. I am basically glued to a reference frame which is that uniform flow, and so I get u total as u, and then P total would basically be whatever is the pressure that is there. So, now if I write down my equation for the disturbance and ignore all the nonlinear terms, so I am still going to assume that disturbances are quite small. So, assuming that all the nonlinear terms are ignored, I arrive at an equation which is dou u dou t minus 1 by rho grad p plus nu del square u is equal to, I mean that is the equation, my linear version of Navier-Stokes, and then divergence of u is equal to 0. What is the boundary condition at r equals a and as r goes to infinity? At r equals a, what is the boundary condition? So, in the lab reference frame, the boundary condition is the particle velocity. In the uniform flow reference frame, perfect. And what is it at infinity? Zero, right? In the reference frame moving with the uniform flow, u is equal to 0. So, that is your boundary condition. These are the equations which you need to solve. So, now this equation is identical to the unsteady Stokes flow problem that we have done, with just a change in the boundary condition. So, earlier we said u is equal to u bar of t, right now we are going to say u is equal to u bar minus u infinity, but finally the entire quantity is purely a function of time. So, you are just changing what is the velocity with which the particle is actually moving. So, the particle moves with the velocity u bar of t, right now you are saying it is u bar of t minus u infinity of t. So, there is a reference value with which it changes. So, now if I write down the expression of force, you are going to get minus 6 pi mu a. What is the quasi steady Stokes drag? This is a sphere moving in a background uniform flow, right? So, what is the quasi steady Stokes drag? Correct. Nothing changes regarding this. Then comes the added mass term. This would be, let me write it, okay, du bar dt minus du infinity dt. So, this is a sphere which is accelerating in a fluid which is accelerating with a constant speed. So, it is the relative acceleration, that is what the added mass term would be. And then you have your so mu a square by, let me put it inside, minus infinity to t 1 square root pi nu t minus t prime all of this evaluated at t prime dt prime. Will you have anything else? I have just taken whatever was there before. This was the expression which we discussed with some detail in last lecture, and now I am saying that it is all written with as a relative velocity or relative acceleration. Now, to answer if there is anything left, you have to go back to your fundamental definition of force. So, what is force acting on the particle? There is a non-ambiguous definition of force acting on a particle. What is it? Right. This is not, I mean, whether you do low Reynolds number, high Reynolds number, doesn't matter what you are doing, right. Now, what is sigma here? It is the stress tensor, but what is it? What stress tensor is it? Is it the total stress tensor or is it the disturbance stress tensor? It is the total stress tensor, which can be written as the imposed flows stress plus that due to the disturbance. So, what we have written down here, this is actually the part which is the disturbance part. That is the force experienced by the spherical particle due to the disturbance velocity. But there is also a force that is experienced by a control surface which coincides with the sphere due to the undisturbed flow. So, sigma dot NDS, I could write this, if I use a volume integral, what would it be? So, sigma, if you write down your expression for sigma in this particular problem, you can write this in terms of a divergence, and then if you substitute for what is divergence of sigma infinity for the background flow, divergence sigma infinity is minus grad P infinity, right. Sigma infinity is, for it is a Newtonian fluid, we are not making any other assumption. So, it is minus P delta plus 2 mu E infinity, and the background flow is a uniform flow. So, there is no rate of strain for the background flow, which means the background flow only has a pressure gradient. So, this particular term can be written purely as del P infinity. I can convert this surface integral into a volume integral, which is the sphere. This is Vp. So, you have the sphere of volume P, surface P, Sp. So, I am converting this into a volume integral, which is divergence of sigma infinity dV, right. And so, this is divergence of sigma infinity evaluated in a control volume, which is basically occupied by the sphere. So, the way to think of this term with a negative sign, the way to think about this term is, this is the force that would be imparted by the background flow in the region that is occupied by the spherical particle. If there was no spherical particle and you identified exactly the same region which is occupied by the spherical particle, there will be a force acting on that spherical particle by virtue of the fact that the background flow is not constant in space and time. So, in this problem it is not constant in time, it is accelerating. Because the background flow is accelerating, you require a pressure gradient, because the background flow is not existing in a random space. It is also a solution of Navier-Stokes equation. Until now, whenever we said u infinity, we really were not trying to be very specific regarding what equation does u infinity satisfy. We said, okay, I mean linear flows and uniform flows, so we are considering sufficiently simple flows. But right now what we are doing is we are trying to be a little more specific, saying look, the background flow is a solution of Navier-Stokes, and if the background flow happens to be an unsteady uniform flow, then it requires a pressure gradient or it requires some external forcing which has to balance the acceleration. Otherwise, what will balance the acceleration? Now, that external forcing or pressure gradient, when evaluated on the control surface, is going to give you a contribution, or integrated over the volume of that sphere is going to give you a contribution. So, that is what we are saying. So, if this particle size was small, I can approximate this, or I can write this as the pressure gradient averaged over the particle volume. Okay. Either I can treat it as small and evaluate it at the center of the particle, or I can also write it as a pressure gradient, that is volume averaged over the sphere. So, which means in your expression here you require an additional term, that is this. This came about because you have now said that the background flow is no longer constant in space and time. So, this equation is known as the Basset-Bossinesq-Oseen, in short BBO equation. And I think this term, this particular force which comes a lot also in wave hydrodynamics, is known as the Freud-Kurloff force. That if you have like a wave field that is there and you are trying to find out what is the force a structure experiences purely due to that unsteady wave field, you would be evaluating this particular term. But the BBO equation that you have here, the Basset-Bossinesq-Oseen equation, is an exact equation at low Reynolds number for a spherical particle that is subject to a uniform flow which is constant. Obviously, by definition uniform means it's constant in space, but varying arbitrarily in time. So, this is your Basset-Bossinesq equation where we had u as a function of time. Now, what if u infinity was a function of x and t? It was not just a function of time, but it was also a function of spatial coordinate. So, now there is no such thing as a coordinate system that you could move to and only inspect the flow, because the background flow is non-uniform. So, we will just stick to a fixed coordinate system, but before that you need to actually take note of the fact that the background flow is now a solution of Navier-Stokes, right. So, if you want to find out the contribution from the background flow, let us say the undisturbed flow, if I use the notation u to say that that is the contribution acting on the spherical control surface due to the undisturbed flow. So, which is equivalent to doing a surface integral of sigma infinity dot n ds over that spherical surface, and this can be converted to a volume integral of divergence of sigma infinity dV, right. You have the spherical particle, you are now doing a volume integral over that particular sphere. So, it turns out into divergence of sigma infinity. Now, what is divergence of sigma infinity in this problem? So, here you have to be careful, because sigma infinity here is minus p Kronecker delta plus 2 mu E infinity, right. So, you can't just be taking pressure into account here. So the divergence of sigma here infinity or divergence of sigma infinity is rho du infinity dt minus g. This is the fluid acceleration. This term is your acceleration due to gravity. So this particular term I can write now as a volume integral of grad p infinity plus mu del square u infinity dv, which is a volume integral of rho du infinity dt minus g dv. So even if the flow is not unsteady, but the flow is varying spatially. Think of a flow which is spatially non-uniform, and we all understand when we get introduced to the idea of a material derivative that a fluid can have acceleration even if it is steady. If you have a velocity field that is varying in space, you can have a non-zero contribution to the u dot del u term. So this du infinity dt is dou dou t of u infinity plus u infinity dot del u infinity. So you can have a contribution to your force acting on the particle that comes from the fluid acceleration of the undisturbed flow. So this was the undisturbed part. Now we move to disturbance. So the disturbance equation u total is u infinity plus u, p total is p infinity plus p, and obviously sigma total is sigma infinity plus sigma. So everything is split in terms of the background flow and the disturbance. So if I were to now write down the equation for the disturbance and linearize my equation, the equation continues to be something that we are quite well acquainted with. Subject to the boundary condition. What is the boundary condition at the surface of the sphere? If the sphere is moving with a velocity u bar, what should be the boundary condition on the sphere surface? What is it? It doesn't change from what you just did, right? It stays the same thing. Just because the flow has become non-uniform, the boundary condition is not going to change. The boundary condition is still going to be whatever is the translational velocity of that spherical particle minus u infinity, obviously evaluated at the surface of the particle, and then I have this to be 0. Now this equation is again quite similar to what we have done, right? This is still the same unsteady Stokes equation, nothing particularly changes about this equation. And if I have to compute what the force that the disturbance, so the total force is the undisturbed force plus the disturbance. We have already evaluated what the undisturbed force is. The disturbance as a function of time is what we need to compute from the unsteady Stokes equation subject to these boundary conditions. So what should be the contribution from the disturbance? There are only 3 terms. We have done this, right? The Basset-Bossinesq-Oseen equation and even earlier the problem, all of this is building on this. There is a quasi steady Stokes drag, there is a added mass term, and then there is a history term. These are the only things that are there. But there is an important point you need to realize here. The point is, let us focus on the quasi steady Stokes drag. Where is u infinity? U infinity is a spatial function, not just a temporal function. So, when you are calculating the quasi steady Stokes drag, where do you evaluate u infinity? It is quasi steady, so obviously it should be whatever is the time instant when you are finding the drag. But what is the spatial coordinate where you need to find u infinity? On the, where on the sphere? At the center, on the surface? If it is on the surface, which point on the surface? If you say center of the sphere, are you making any error? Recall, if there is a sphere which is moving with a velocity u and it is in a background flow u infinity of x, what was the drag force and how did you find it? Obviously, if u infinity is a constant, then the drag force is trivial. It is minus 6 pi mu a u bar minus u infinity. What happened when u infinity was a function of spatial coordinate? That was basically the point of deriving Faxen's relation. So, either you can write it with the Laplacian term or you could write it as u infinity averaged over the surface of the sphere. If you remember this also from the question you had during your midterm, that if it is force free, the object should move with a velocity which is the background velocity integrated over the surface. So, that is what I am saying, it is averaged over the surface, 1 by 4 pi a square surface integral of u infinity. So, this drag force is not the velocity of the undisturbed fluid at the center, but rather the undisturbed fluid averaged over the surface of the particle. If you evaluate it at the center, you need to include the Faxen's correction, which is basically then doing a Taylor series expansion and finding out that there is a Laplacian term that comes about. So, whichever way you write it, I am going to write it as a surface average. You can write this also as u infinity of 0 plus a square by 6 Laplacian u infinity of 0. Right? You can choose whichever way you want to write this. So, for a spherical particle, that surface average becomes directly a two term expansion, velocity and Laplacian of velocity, but otherwise you can treat it like a surface average. So, similarly, if you go back to the root of your so that is your Stokes drag, and then your added mass term, that would be minus half added mass du bar dt minus du infinity d volume average. So, the added mass is the fluid acceleration integrated over the volume, and then you have your history term, which is 6 pi mu a square minus infinity to t 1 by square root pi nu t minus t prime du infinity surface average dt minus du dt dt prime. This is at t equals t prime. So, because the flow is varying over the length scale of the particle, which is why I am introducing these averages. Now, obviously, if the background flow does not vary appreciably, then you can replace these averages with the velocity of the background fluid of the background flow or its acceleration evaluated at the particle center. So, you have now Stokes drag, added mass, history, and then the undisturbed force or the force acting on the sphere due to the undisturbed fluid. So, writing all of it together, either you write it in terms of acceleration or you can also write it in terms of your divergence of sigma. So, this is if there are no additional forces acting in the fluid, then it is this. But if there is any additional forces acting in the fluid, then there will be terms that will come, but this is an exact term because this is divergence of sigma, right? That does not change. Sigma I should put here all infinity, not C, infinity. So, that is the viscous stress for, or that is the total stress for the undisturbed fluid, its divergence evaluated of the particle surface, a particle volume. Then you have the quasi steady Stokes drag, then you have the added mass term, and in the end you have the history term. This equation is known as the Maxey-Riley-Gattignol equation. They came out in two papers at this on this same year 1983. One was Maxey-Riley's paper and the other was the paper by Gattignol.